Welcome back to the last part of our optimization lecture. In this part we will just have a look at the computation of gradients and how you can do this in a more efficient manner than just calculating the partial derivatives all the time by yourself. So one of the central things which we'll be discussing or which we will explore is the chain rule. But first of all, let's have a look at the definition of a gradient and maybe its generalization to higher dimensional vector spaces, to matrix spaces, for example. So gradient descent needs a gradient. And if we want to define the derivative of a function which maps a matrix to a real value, then we can do this in two ways. And the first way is here denoted as the Jacobian, and the second way is denoted as the gradient. And the Jacobian is the transpose of the gradient and vice versa. The Jacobian maps here the n times d dimensional matrix to a d times n dimensional matrix. So you see here that the dimensionality of the input space of f is swapped. And the gradient has this nice properties that if you map to the space of real values, that the gradient has the same dimensionality like your input space. And this is also why you can make a gradient descent step. So you can just say x minus some step size times the gradient, and this is then well defined. This has the same dimensionality. For the Jacobian, we would have to transpose it. And how do these things differ in matrix notation? So it's basically the same. Now we have here the more general case of a matrix. So instead of having just one vector, we have here all the matrix elements x1, 1 until xn1. And here we have x1d and xnd. So basically we take all the matrix elements and derive the partial derivative to it. And for the gradient we have here these partial gradient terms. They are actually ordered in the same way as they are in the matrix. Now this notation is not used by all authors, so be careful when you read some related literature. It might be very well that then another notation is used, but most often this is the used notation, and it's also consistent with the ideas of gradient descent. So the gradient has to have, for example, the same dimensionality as the input space. Let's have a look at the cases for the Jacobian of f. So if we have here a function which maps from a vector, a d-dimensional vector, to the real values, then the outcome is the transposed vector. If you map from an n times d-dimensional space to the real values, then the dimensionality of your Jacobian swaps the dimensionality of the input matrix space. So what has been n times d-dimensional now becomes d times n dimensional. And so if you have a look at this lower part here, this is basically equal to the definition of the transposed of a matrix. Now the only thing which is nice, or when the Jacobian is maybe a bit more intuitive, is if you map from the real values to space to the to a vector space. For example, here the space has c dimensions, and then you see that you get here a vector which has the same dimensionality as your output space. And if you map from a d-dimensional vector space to a c-dimensional vector space, then you see that here the dimensionality of output and input vector space is swapped. So here it was basically from d to c, from d-dimensional space to c-dimensional space, but the Jacobian has a dimensionality of c times d. Now you see here, for example, for the function from the real valued space to the c-dimensional vector space, that we have here the vector, so we always compute the derivative subject to our one-dimensional variable x, but we have here c functions. For example, f from just one point x, and then you define f usually as f1 from x until fc from x. And then you have to apply the partial derivatives for all of these functions. When we have a function which maps from a d-dimensional space to a c-dimensional space. There you see that the partial derivatives are basically running here in the denominator from 1 to d horizontally, and the function indices are here vertically ordered. And the same we can do with the gradient. So a lot of these definitions of the rules for generating a gradient, a lot of times you will just puzzle it together such that the dimensions match. And in most of the cases this will be fine. Yeah, we will see this later with the chain rule, for example, how you have to puzzle together these elements of gradients and Jacobians. So let's go through the examples. So we have a function f from a d-dimensional vector space to the real values, and then we get as a gradient a d-dimensional vector. And if we have a function which maps a matrix to the real values, then the gradient has a dimensionality as the matrix. And if we have a function which maps one scalar to a c-dimensional vector space, then the gradient here is now a transposed vector, so it's like lying here, and the indices of the function are varied horizontally. And if we have a function which maps from the d-dimensional vector space to the c-dimensional vector space, then we also get as output a gradient which has the dimensionality of d times c. Okay, keeping this in mind, that the output of the gradient has the same dimensionality as the input space for the most relevant cases. Now let's have a look at the derivation rules. Now we already said that the gradient is actually the transpose of the Jacobian. This is mentioned here. And then we also have something which is called linearity. So the partial derivative of the Jacobian is a linear operator. You see the operator of del over del x as a function. And linearity says that if I scale my argument with the parameter alpha and I add my argument with another argument, then it's the same as if I scale the function value of this first argument and I add the function value of the second argument. And we have the chain rule, so if we have here a concatenation of functions and we want to compute the derivative, then this is equal to the derivative of f subject to g. This is like the outer derivative, and we multiply with the inner derivative. So in order to get this multiplication done, because in most of the cases, and I think also most researchers don't recall by heart the chain rule. They just know that you have to multiply the outer with the inner or the inner with the outer, but who can actually remember all the time like what this order was actually like. But in most cases only one of these directions makes actually sense, and this is then the direction into which this multiplication here between the outer and the inner is actually defined. So everything you need to know to become fast in calculating gradients and to not perceive this as an inherently difficult task is to remember what the dimensionality actually is of a gradient, and it's the same dimensionality as you have from the input space, and that the chain rule is just outer times inner or inner times outer, and then you have to puzzle together which way it is, and that you can apply the linearity. And if we know now these rules, then as an exercise I would ask you to derive the following derivatives. So the idea is that for the first derivative, this is a Euclidean norm, you can do this by the definition over the partial derivatives. But then for the later derivatives we can apply one of these rules. So for example, for this derivative here where you have a vector b and a scalar a and a vector x, and you want to derive the derivative subject to x, then you can apply the linearity. Now for this third derivative we can partially apply the linearity, but also we need to know what the derivative of the matrix A times x subject to x is, and this you can only derive by going over the partial derivatives once more. And the next exercise would be then to determine the gradient, where you compose now the norm, for which we already know is derivative, and the derivative of this affine map, b minus ax. And then we go big here. So here we have now a gradient subject to a matrix. Don't be afraid. A matrix is also just something like a vector. But the principle is the same. So have a look if you can find the derivatives of these equations, and you can look then the solutions up in the accompanying math PDF. But we will also have some discussions about this in the lecture slots. Okay, I hope you feel now that you got an idea about how to approach an optimization problem. This will be a recurring theme in our lecture. So it's good if you have down the basics, but yeah, as with linear algebra, it's not important that you understand now everything directly and that you know everything, but it's just to give you a short introduction. Okay, I hope you have a nice day, and then see you next time.